This is a presentation for my dearest brother, Jean-Paul van Bellen. He's a professor at Cape Town University. He's much more of an expert in IT than I am. And he just took a sabbatical to work on his favorite project, again, I would say, and that's artificial intelligence. We were in touch on that, 10, 15 years ago. Our interest in the topic is quite different. I'm more interested in the practical applications. He's really interested in sort of the machinery of it. So now that he's starting again, I'm putting this video because I know if I talk to him on the phone or something, he'll interrupt me every 5 seconds, and so I want to develop my train of thought. So what we have now actually is these chatbots, right? ChatGPT from OpenAI, in which Microsoft has invested very heavily. Copilot, also Microsoft, replaces Cortana, which never really worked well on Windows, but I kind of liked the female voice because I'm a male. And then, yeah, it did guide you around, and it used some tools about which I'm going to talk later, speech recognition, and yeah, I was impressed by it. But so now we have Copilot. We have Bart, Google's response to ChatGPT. Yeah, I think sort of Bart is behind also. I bought a new mobile phone, and I also like, the Google Assistant on it. It's great. These tools have really come along quite far. I don't know Llama. Apparently, Meta's chatbot. I don't say that derogatively. I'm going to talk about that actually. I'm deeply impressed by these things. These things are powered by yeah, what they call language models, which are interesting, and I'm going to contrast the approach to sort of formal logic, the kind of things that I was taught 30 years ago when studying philosophy and all that. The tools and interfaces, that's probably what impresses me most, and probably, as an ICT professional, also in terms of, yeah, the APIs you can build with them as a business. I mentioned speech recognition. That's so much better now. You talk to Google Assistant, indeed, it really does understand what you say, and I'm contrasting it to a number of chatbots that you have on websites where, honestly, you really get annoyed because it takes you ages to explain what you're looking exactly, or what you're looking for in the documentation. For example, I mean, as one of the functions, or if you need help on a problem, it takes forever to sort of to direct you to the right person. Translation. My girlfriend is Chinese. We converse through Google Translation most of the time, from English to Chinese and Chinese to English, and it works great. Very fast, very accurate. And not kind of simple. We can have very, very deep discussions. What is very impressive is the text to image and image to text, like these tools, DAL-E, I don't know how you pronounce it, that comes with ChatGPT, at least if you have a paid subscription, which I have, $20 a month, it's really worth it. So I'm very impressed. We're 2023, and I'm going to talk about some ideas I had 10 years ago. All these ideas have been implemented, and in a way, much better than I ever thought they would be implemented, or at least I thought it would have taken a lot more time to do that. Wikipedia sort of says, the secret of these things is indeed these language models, called large language models, because it can cover, well, I guess I don't know why they call it large, but cover various domains. You can talk about math and physics and science, and you have all these stories now about chatbots being used for psychotherapy, and there's so many applications, so that's probably why it's called large. It can combine various domains of knowledge, I would say. But the main thing about these language models, which I mean, I'm not a specialist, not at all. But yeah, roughly speaking, Wikipedia explains that as these systems learn, they're learning systems, and they learn by establishing statistical relationships between text objects, I would say, because they do it from text documents. It's computationally a very intensive process, which I can imagine, because I will talk a little bit about that in 15 minutes or something. How these things may or may not work in terms of bits and bytes in a machine. And it's a self-supervised or a semi-supervised process. Self-supervised probably means that it checks, its outcomes against similar similar outcomes by exploring even more sources. Yeah, I would like to dig into that, but I'm not going to do that. The only thing is sort of this thing is something, there's a lot of talk about regulating AI, but you would have to deal with this problem. Like we cannot prevent these systems from learning. Like we want them to learn. The only issue about regulation is probably what is reflected now in this class action lawsuit from the New York Times against OpenAI. And that's, indeed copyright issues and what kind of sources can you can you use as a system to learn from? Can you use something you learned with an individual user in a conversation with another user? These are all tricky. I wouldn't call them moral questions because they aren't, but yeah, legal questions, and that's for me the only thing that probably needs to be solved in the coming year, the legal issues around AI. Regulating technology, I'm not a believer as such. Why? Because regulation is to make certain things good or bad, and technology in itself is neither good or bad. It can be used for bad purposes. Drones and other killer robots are already being used by armies. You're not going to stop that. On the contrary, I think if you regulate AI in the civil sector, well, then it means that the military are going to just produce more and more powerful systems that are going to be used for bad rather than good purposes. So this definition is incomplete. I'm also saying it because I did experiment with ChatGPT and I was very impressed. I was a bit negative, I think, in my previous conversation on what ChatGPT understands. What its understanding really is. What is understanding something? But yeah, it's clear ChatGPT understands an expression like this one. This will probably be Chinese for most of you. It isn't for me. It's just a four-vector expression of Maxwell's equation, and it's very beautiful because it's all of the electromagnetic theory is in that one equation. You need to understand it with another equation, which is implicit. That's the charge conservation law, which you can formally, logically write like this. So yeah, we have powerful mathematical symbols here and a system of symbols with relations, lots of mathematical operations, but these also incorporate, and this is the thing when you want to understand these equations, they incorporate a lot of mathematical dimensions and operations, or operators, I would say. But these operators act on things that have a physical dimension. And once you understand that, it's a very beautiful representation of what reality is. This will sound like Chinese. I'm just highlighting it because, I can have conversations with that on ChatGPT, and it sort of does the trick to a certain level. It parses these equations correctly. When I ask specific questions about it, about what does it represent, it answers these questions correctly. And so, in that sense, it passes the Turing test. Turing test said, if you're conversing with a machine or a human being, can you tell the difference? In a way, it does not pass the Turing test because the ChatGPT comes back so fast that you say it's not a human being. Obviously, it understands things much faster than anyone else. I would try to ask for help on an equation or try to explain something that I deeply understand. Um, I had something. Yeah, this is also something very wonderful, and this is where I think I tested the limit of the system. It can also parse. I studied a bit of quantum physics. It can really parse wave equations. There's various wave equations around for example, representing free electron or an electron in free space. Same thing. There are no other charges around. I'm not going to go into the detail because will sound a bit ridiculous that you need such complicated equations to represent something that is um, something very simple in the real world. But we have Dirac's equation, Klein-Gordon equation, Schrödinger's equation, Schrödinger's equation in free space, not for the hydrogen atom. And it can parse these equations. The thing where it got into trouble for me is that, I had a paper on that, and I think Schrödinger's equation is the correct one, and Klein-Gordon, there's assumptions there that don't make sense to me, especially in Dirac's one. Wave equation, and that's sort of where the thing went. I can parse these things, so I understand them, but where I had to basically say, look, our conversation doesn't make sense anymore because you do not understand what I'm really talking about. What is true in a sense of what is a theory that makes more sense than another theory. And all these theories are consistent in themselves. It's just different assumptions, and that's where ChatGPT I think didn't lose it. It was very friendly, but it admitted like okay, what it basically told me what I had told it. Let's think about it, and then we'll try to make some sense of this paper again at some point in the future. But that's great, and that's incredibly impressive. One thing I want to do also, and this is a bit of a joke, if you really want to read something very nice and concise on, how logic, symbolic representation of systems really works, and what the beauty of equations, when we say this equation is beautiful, what it really means. And this is this U is equal to 0, and U is a multidimensional matrix. You'll say that doesn't make sense. But this is an equation. Feynman is right that he calls U the unworldliness, but it's maybe the worldliness. Yeah, this equation represents the world. Because you can break it down in a number of, a sum of a set of other equations, which is about the sum symbol, and then E would probably, it's not a one-dimensional index, but 2, 3, depending. And you can break it down, and then you can insert, Maxwell's equations, the Planck-Einstein relation, a lot of other equations. And so when you expand this thing correctly, you will have all the equations that we know to be true from experiments, all summed up in this U is 0. And so Feynman, I'm not going to quote him literally, but he talks about the beauty of equation X, this one or this one combined with, its quantum physical equivalent, is blah, 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 blah. He calls it a trick, but in the end, I prefer to call it the beauty of these equations are its simplicity and the fact that in our mind, we can directly and immediately associate these very simple expressions with, magnificent systems of reasoning and equations and, the history behind stuff in terms of discoveries that have been made. And that's very beautiful. Okay, I'm rambling a little bit, but it's okay. I hope my brother will continue to listen. Um, to go to something else is I said, I think if you want to understand artificial intelligence, I think you need to combine both these language models, or yeah, how a child learns a language. That's sort of what we've programmed into these systems. A child also learns its language by listening. In this case, the chat this system will read text and parse it. A child will do the same when it listens to its parents. It hears a lot of sounds, and it will parse these sounds into things that have a meaning, and it will make associations. Blue fits with things that are blue. I will talk about that a little bit later, about what it means, what's the meaning of blue. And so the difference with a child is that probably their mechanics are different. We are physiochemical systems, I would say, while a computer is, yeah, it's bits, zero and ones, and then a lot of programming logic that you apply to these bits, and it learns faster, as at least now, because yeah, the computational resources are there. 2, 3, 4 gigahertz clock speeds, number of logical operations per second. That's amazing. I don't think our brain reaches those speeds, but it does things differently. But the outcome is that it does things better than we do. And I started thinking about that, and that's what I'm gonna quote. Let me first clean up a little bit my whiteboard. About 10 years ago, 2012, 2013, I wrote a blog which was the Turing tests, plural, because I said, ChatGPT passes the Turing test easily, and then at the same time it does not, exactly because it passes the Turing test so quickly. It's fast, and then if you really push it into areas of specialized knowledge, like I've done that on these wave equations, then you clearly feel like you're just mimicking, you're emulating or simulating. You're just like a student who sort of gets it, but not quite. And that's where the professor would give him a 16 instead of 18 on 20 or 20 on 20, because he said, okay, you studied well, you've memorized well, you make the right associations, but it's not good enough to give you a perfect score. Part one was written till 2013, I reviewed, and that's about the societal impact of what I then called artificial genetic intelligence. We have a generative intelligence, which comes out of that closed box of a formal system by using these language models, or general, what I call the genetic or artificial genetic intelligence, because Turing test was about a Turing test. And once you pass the Turing test, you can use, once the machine passes that, you can indeed use it, and that's what I explore there for, therapeutic purposes. I start the story actually referring to my own experience, having worked in Afghanistan, coming back and trying to adapt a bit to a different society. And so, yeah, chatbot is useful. The story was also partly inspired by a story on which I think the New Yorker did a nice magazine, a man who fell in love with a chatbot. He was looking for a Russian bride, and he didn't notice that during 2, 3 months he was basically talking to a chatbot, and he had developed emotions for her. And that has, when I watched the movie Her, that came out in 2013. Thought, well, they've copied part of my script, but they can't have, because, of course, a lot of people thought the same. But have a look at that thing, because it also goes into, how to use artificial intelligence in business. And it already then talks about, how a lot of knowledge workers, computer programmers, but also basically administrative stuff, processes where the business rules are complicated, but can be automated. Yeah, will be automated. So that's the automation of the automation, I would say, or the substitution. We had, first, second, third. industrial revolution where industrial workers were replaced by robots. I think we are entering now the phase where knowledge workers uh, are going to be replaced increasingly by artificial intelligence, and that's something inevitable, something to be worried about probably, but probably something you cannot not really regulate, and you must trust the adaptive capacity of people to adapt to that. um, Part two, I started doing that last year, but then I thought about Kubrick's story, 2001 Space Odyssey, which goes back to 1968. Asimov's books from the Second World War, where you have sort of these scenarios where intelligent robots work together with human beings and explore space. We had the Mars One project. This is a theme that Elon Musk explores also with his SpaceX, and my idea is really, sending human beings on a space journey that's going to last. The nearest exoplanet is like 4 light years away. So even if we would could build a ship with reaches a fraction of the light speed, which we can't, then it's going to take like 30, 40 years, and you're talking, probably families that you need to put on that craft that are going to reproduce. So it's probably safer to send artificial intelligence into space and have them report back to our grandchildren, because humans have emotions and this and that, and that's where it goes wrong in Kubrick's movie, and that's where I think it would go wrong in reality as well. So have a look at that, because I think these are the most interesting things. They're fun to think about, and it's the kind of stuff on which you can base a movie. Let me now talk about why formal logic, propositional logic, I will call it. Well, propositional logic is just one formal system of logic. We have a proposition at P, right? And then we're gonna play with that. And we did that 30 years ago. There's a lot of stuff out there. The problem starts right there, actually, where we make abstraction of real life statements, I would say. Such as, I quote some there, it's a blue moon today, or I'm feeling blue today. Earth is a blue planet. So we all say these are statements. And somehow the assumption is that these are atomic statements, that they stand on their own. And that's already where 30 years ago I thought this can't represent a real language system, this formal propositional logic, because you talk about it's a blue moon today. I'm feeling blue. Earth is a blue planet. So you already see that blue is one string or one set of symbols or one symbol. And so you see blue has quite a different meaning depending on the context. If I say it's a blue moon today, we know it's an exceptionally large moon. I'm feeling blue refers to a sentiment that's related to the blues as music. Earth is a blue planet, yes, but what kind of blue? It's not only blue. There are clouds. There's white. But it has a lot of oceans, and these oceans give the Earth a blue hinge. So, what's the meaning of blue? A physical definition would be very different. That's in one of the primary colors in the RGB system. We can also talk about pigments. A bright blue pigment that I think 2-3 years is I forgot for which these elementary chemical symbols stand. But so yeah, if you put certain chemical elements together, you will have a crystal or whatever it is that has a particular shine, color, reflects differently, and that will probably have a spectrum that is blue, and a particular spectrum, because this pigment, if you will go Google it, it's very bright blue. It's beautiful. We can also say blue is the light that gets emitted by a blue laser diode, and that would be in the range of around 445 nanometer. So blue, 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 blue. That's all blue. Yeah, you see, blue has a lot of meanings. So that's already where this system where you say like, okay, I'm gonna talk about P, and later we're gonna talk about U, R, and we're gonna combine this in sort of logical operations on them. Yeah, but maybe we start off the right footing here. I talked about that. We can have much more complicated prepositions. This, for instance, I said ChatGPT will understand that as a heat diffusion equation, or just a diffusion equation in general. Sorry, I'm suffering from a cold. So, but yeah, if you look at it, you can ask GPT, it will have to come with some text and say this is a diffusion equation indeed, describes heat flow. We'll show this is a symbol, that is the gradient, this is the temperature, a scalar function, this is diffusion coefficient, and this is a heat flow vector. Combined with that, we have a conservation law. If heat flows out, the total heat within the object will diminish over time. So lots of stuff, but you can immediately see that these and this one, they're not really independent. So if we call this one P and Q, and we say either P or Q is true, it just doesn't work that way. These axioms are related, the symbols are related. Operators come back in other expressions. So we have really a system of meaning, I would say. I will talk about Wittgenstein in a moment. So let me do that now, actually. I think Gilbert Ryle added a lot to the discussion on these formal systems of logic and how do things acquire meaning, by pointing to straightforward category mistakes. If I say something like this, the gradient of T broke its leg this morning, then you will say the gradient of T is a mathematical symbol that indeed reflects perhaps a diffusion process, but it doesn't break its leg because it doesn't have any legs. It's not a human being. So we should avoid in a system like that statements like that have no meaning, that cannot have a meaning whatsoever, because you will get nowhere. It's garbage in, garbage out. You will say that's obvious, but Google it and look it up. Sometimes it's not easy to sort of say this is a category mistake or it is not. I will give an example. God is dead, right? I can interpret that if I'm religious to say, oh, God, God exists and he's eternal and he cannot be dead. So this is a category mistake. The category of life and death doesn't apply to God. So for a religious person, this is a category mistake and discussion is over. For me, it has meaning because I'm not religious and God is dead. It comes from Nietzsche, and he clearly meant something with that. He pointed to the fact that religion generally is losing its importance in society, which is a question that is up to debate. I think it's regaining importance, but in any case, it means something. It's not a category mistake for me. So things, it's easy to do some philosophy and develop some definitions, but it doesn't always fit into these nice philosophical schemes like the one that Ryle developed as an analytical philosopher. Semiotics and linguistics. Semiotics is the sort of the science of science, I would say, semiology, de Saussure called it, and linguistics is the how do science fit together into a language. And we know that de Saussure made, I think, a very big country by distinguishing, when you look at a sign like T, the secret to understanding it is that T is a T. It's a symbol, but we could have chosen another one, maybe T like that, but we use that for time, so we prefer a big T. Le the signifier, or in French it sounds better, le signifiant, the symbol itself, you need to, that always comes with what it means. And so once you understand that, this dual nature of a symbol, then, yeah, formal logic may or may not make sense. In the case, it's going to make a lot more sense than, talking about the night in which all clouds are equally black, as Hegel once said when referring to Scheller's philosophy. So yeah, then we have indeed, we avoid some of the problems above when I talked about blue, because we realize that, yeah, okay, blue is blue in its context, like just like this T is a T, like in the T of a word like time, and time is like, okay, Time magazine, or just time as a physical quantity. And the gradient of T, the gradient of temperature, T as in temperature. Once we understand that every symbol has this dual nature of the symbol itself and the meaning that comes with it, and then you can refer to context, then you can say, yeah, okay, I understand why combining these statements or symbols in a logical system should generate meaning. So that sort of should bit debunk what I said here. Propositions don't make too much sense. The problem still remains the same, and here I'm going to talk about Wittgenstein as promised. Let me clean up my. Wittgenstein once sort of thought that we can really develop such a formal system of logic with a sort of atomic propositions, things, statements that are independent, stand on their own, and then we combine them and we can develop an unambiguous and I've emphasized that monovalued propositions, and then we can combine them in logic. So he developed this Boolean logic, well, that was around, but these truth tables, and I will talk about it in a moment. But yeah, he said, so in this system we can have a P and a Q, and this P and Q will both have a meaning. We're not really interested in the meaning, but they're surely not meaningless. We don't have any category mistakes. And then we can assume that P and Q are either true or else false. It's dichotomy is the XOR condition about which I talk. It's a logical operator in itself. This does not imply that we need to that we know their truth value. This is I've got a paper on quantum logic around. There's a big difference between developing a formal logic system like that and claiming that you know everything, that you know the initial conditions of the system, that you know where things are. There's a big difference between knowing everything, what could possibly be true, and having a system that allows us to predict things as they're going to happen. In quantum logic, we know that it's statistical determinism. So you can have a system that is deterministic, but at the same time allows for statistical variances, because we do not know at the smallest of smallest levels where a charge is when it's orbiting around a nucleus. I know this will sound like Chinese to most, but I said I'm doing this lecture for my brother, so I know he will play with these things and understand them very easily. So before I go into because now I said, like, okay, we can start with saying, a proposition P and sort of an atomic statement like that doesn't make much sense when you think about how we really use language and how a language system generates meaning. I'm not going to talk about sense. Sense is philosophical, spiritual, but meaning, it means something to us. And then I sort of said, like, okay, with semiotics, linguistics, yeah, we can go back and propositions do make sense. I just want to highlight and be skeptical again. This is an example of the difficulty of I would say, parsing natural language to a formal system of statements. This is this question: was Napoleon good or bad? for Europe. I'm a European. I'm a Belgian. Belgium would not have existed without Napoleon. Belgium was the outcome of the Napoleonic Wars. Is the existence of Belgium good or bad? I think it's good because I'm a Belgian, right? But for a Frenchman or a Dutchman or a German or he went to Russia, we can. They will all wonder like, oh, Napoleon probably was quite bad because a lot of war. But it's a legitimate question and it's a natural one and it leads to nice discussion. One of my uncles, he's unfortunately dead, was a specialist, a historian who knew an awful lot about Napoleon and he would love these kind of questions. And he say, yeah, Napoleon was good because look at it. He introduced the civil code almost all over Europe. And when you look at it at the long term, that's probably a reason why Europe is now rather well integrated because we share similar legal systems. Of course, yeah, there were bad things about it, but these wars, there were a lot of heroics also, and then maybe there was maybe the UK or Germany were becoming too powerful, so it led to a restoration of the concert of nations, as it was called in the 19th century, balance of power. So I mean, there's so many pros and cons. The thing I do not want to answer the question was he good or bad. I just want to show you how difficult it is to parse this into a formal system. We would have a statement P: Napoleon is associated with good, okay, and Q is Napoleon is associated with bad, and can be the consequences of his actions. Probably yes. What did he do, and how this result or output of what he did contributed to a system in which people are better off applying a utilitarian definition of what is good or bad for society. But you would say then, yeah, so it's clear, we have Napoleon good, we have Napoleon bad. These are mutually exclusive propositions. If one is true, the other one must be false. Again, you can instinctively feel like, yeah, maybe these are not mutually exclusive propositions because you again then go to what is good. Was the restoration of a balance of power good for Europe, or could he have a sort of a federated Europe much earlier on if Napoleon would have won all those wars? That might have been, we sure didn't want the fascists to win. It would have led to a dictatorship. So probably, okay, let's say, but you see what I'm saying? It's if Napoleon would have won those wars, it would not necessarily have been. I mean, it's difficult to tell. We can't do alternative history. So these propositions, it's hard to say that they're mutually exclusive because what is good and what is bad, everything relates to each other and. The other thing is, okay, let's suppose they're mutually exclusive. We have a very different format. We have a question mark here, right? So we have an interaction between a subject and an object. So the logical statement would be P or Q. And then, we can work out a truth table depending on what you believe to be true or bad about P. Sorry, true or false about P and Q. But this question mark, it brings in that aspect of, social interaction. Language is an expression of social interaction, someone who speaks to someone else. And that you will also never have in that, the systems of propositional logic. Again, I know I'm rambling for most of you, but I don't really care. I said I'm doing this for my dearest brother. To just tell him how I think about these things. So let's continue this development, and we are going to be in this that we can assume that we have P, Q, and these are two statements that have a meaning. They must have a meaning. They're not meaningless, otherwise, and that we can assume effectively that P and Q are binary, either true or else false. So that's an exclusive or condition, as I said. We can. I did a paper on that. We could also develop a formal logical system with three values. It's true, false, or I don't know. but we don't need to do that because I said, in these formal logic, you need to separate the question from um, are their values binary, true or false, and then what I know about them. If I know P is either true or false, and that will be the case with most statements about the world, I don't need to know whether they're true or false. Maybe I can't measure it, maybe I can't see it. I'm just making a hypothesis and modeling a world of uncertainty indeed, where I have, two logical statements, and I'm going to combine them, and that's going to help me to, develop a language that is meaningful and arrives at shorter statements or representations of them and logical operations that out of which I gain more knowledge. So that's it. So we do have a system here, a Wittgensteinian model, where P is associated, I will use the symbol a lot, with a set of two values, true or false. P itself is it's just P. I'm not going to reduce that. It would be one input variable. Maybe I can say that. Okay, let me clean up. I can't write. I said you could develop this in turn. You could say, oh, well, we don't know what true or false is. Well, if you want to develop a formal system like that, just write P is associated with the value true, false, and then some, I don't know. And this I don't know will probably, in the end, be another set of, it's either true or false. And then, you can go, you can indeed then associate probabilities with it, and you can develop a multi-valued logic based on this binary logic. So yeah, it has value, and let's get rolling. We can now combine P and Q in statements like, let's start with the obvious. P and Q. I'm walking in the garden and the weather is really wonderful. Makes sense. P or Q. I want to buy a cat or I want a dog. You will have a preference for one of both. That's very exclusive. Well, I will buy a cat or a dog. I won't buy both. So then we have P itself. I could just say P. That's a meaningful statement. I can say not P. I'm not going to buy a dog. I'm not. These. I'm just saying like there's a whole set, and you will see where I'm getting at. I can also say if P makes sense. Then Q. If the weather is nice, I'll go for a walk. Or if Q, then P. If only P, then Q. So if P happens, yeah, then I'm gonna do Q. I'm really simplifying here, but it makes sense to associate all these things with what I would call natural language. The ones that make less sense, but should make sense, is because now we have about 10. I would say we can argue about the number, but 10 sort of, I would say, ready-made logical operations on these two statements. And yeah, I want to develop some more. Why? I will tell you. Like P, not and Q. And I invented symbols here. Some of them are but I invented. This would be and, this would be or, this would be an exclusive or with a bar. Not is a bar on top of it, or I could also write not P like this. Well, probably like this. An implication, and if only we can show that's a logical. Well, that's a double implication. P implies Q, and Q implies P. Not and, the symbol is logical here. Well, what do you mean? Well, the product, this would produce P, not and Q, or P, we could probably, yeah, also write this. That produces a false if both P and Q are true. You will say, in which circumstances will we need that? I don't know. I could probably find expressions in natural language that would correspond to this logical structure. And I will talk about logical equivalences because that's nice. Well, maybe I can talk about that. Already now, some of these statements that I have here like P implies Q, can be written as combinations of an or and a not condition or a not operator. If I have the not operator operating on P and I combine it with Q with NOR, it's going to give the same truth table. And there I've pronounced the word. If you have, and this is where I want to arrive at this number of 16 possible logical combinations. If you have a truth table, so P can be 0 or it can be 1, and Q can be 0 and Q can be 1, we have 16 possibilities. We put a 1, 1, 1 everywhere, a 0, 0 everywhere, a 0, 1, 0, 1, whatever. For the AND, I said, the whole expression will be true if P is true and if Q is true. Let me clean up my sheet. So we have 16 truth tables here. And this is where we need to have indeed 16 statements, and these very special ones. These are not implications. I actually forgot the term for it. I should look it up. I'm ashamed. Yeah, no, I don't remember. But these 14, 15, 60 are sort of the three very non-obvious truth tables. But as said, these ones, because you can show that we can decompose them in logical operations and combinations of them that do make sense to us in terms of using natural languages. So this is the fascinating thing about it, is that we know that we can create, if we have two elementary atomic propositions, we can create 16 statements, new statements based on P and Q that make sense. Because these truth tables do make sense in all of the 16 cases. Why? Well, it's not directly obvious from these non-obvious logical operations, but if you look at all the logical equivalents, and that's absolutely fascinating, is that this so-called meaningless system of symbols comes with an implicit structure. And based on these logical equivalences, we can formalize what in mathematics would be the group properties or the group structure. Think about the ring. You've heard about these things. The properties of is a logical operation commutative. How does association work? If we put something between brackets, does it differ? How should we put things in brackets? Where do we put the brackets? This whole formal logical system, even as simple as it is, with two atomic propositions, produces a sort of meaning, comes with a structure all by itself. And that's something I found fascinating. I mean, you read Gödel, Escher, Bach. Gödel, Escher, and Bach. I'm referring to this book of Hofstetter. Sorry, I forgot his name for a moment. He talks about, how recursion comes out of logical systems. He thinks a lot about not the Turing test, but what is a Turing machine. He talks about bootstrapping, developing a new language, using an existing language, but adding to the language higher level abstractions and all these kind of things. It all comes back to this, and this is something that fascinates me, but unfortunately maybe I'm too dumb or I haven't spent too much time on it to explore that. But that's actually where in a previous presentation I said, I'm very skeptical about artificial consciousness in that 2013 blog. And let me refer to that again here. AGI, as I call it, genetic artificial intelligence, which is a term non-scientific, not used. I said, it's my way of describing how could we possibly build a system that has a sense of itself, because I think this is the big difference between a computer and us when we think about the difference in terms of consciousness. The computer will never feel pain, or we can't say it feels happy. But at the very, these are elements in the existential sphere, I would call. But I do think, and this is weird to say, that it can develop a sense of itself. I talked in a previous presentation about, the eye, this old Asian wisdom, the eye that sees cannot see itself. Well, that's not true. Intelligent system can have cameras installed and can observe itself. Uh, um, what it does. A robot can send a drone out and see how itself moves on some foreign planet in a science fiction story and whatever. So consciousness, and that is related to that, for me at the very basic, not with pain or love or other complicated emotions that we have as human beings, but with a sense of self. I am here. I'm part of the universe, and at the same time, I'm not part of it. I see myself as a subject rather than an object. And yeah, I'm rambling again, but I said it's for my brother. Um, this would be for me where that sort of sense of self um, might be born. I'm saying it very hesitantly, but we have a formal system, a set of operations, and then we see by this I found metamagical or metamatical, I would say. It comes with a structure. And if I think about, my own sense of self, what am I? Of course, I'm a human being. I'm born on this on that day, but I've got a brain. What is my brain? It's intelligent, right? Can also feel emotions, but intelligence is about structure, and so I found this far more intriguing than Hofstadter's talk about a worm virus that replicates itself. I don't see how replication of a computer program is going to lead to self consciousness or intelligence. Um, but this is something where you have simple ingredients, and this is why I'm also intrigued in by quantum physics. I studied these, how various base states can produce and combine their energy levels and other physical quantities, linear angular momentum. And combine into a system that has a completely different behavior. Well, not a completely different behavior, but has completely different behavior. You can no longer that the system is made up of things that are atomic or elementary, but yeah, an atom behaves completely different than its nucleus or the electron that is orbiting the charge that is orbiting around it. I make a difference between charge and an electron in my theories. And that's absolutely fascinating, I think, where the system indeed becomes more than the sum of its parts. And that's something that's not scary, it's fascinating. But that's something I see happening with these tools that I mentioned, also the chatbots and what have you. They are much more than a part, than the sum of their parts. Okay, let me continue and wrap up. One thing I wanted to note that may be of interest to my brother is there are I said no other exotic statements here. At 16 it stops. And then the whole trick is to make these statements look somewhat less exotic by explaining them in terms of the logical equivalences with these statements. But I said what we wanted to do here is reduce statements as much as we can and used a minimum of symbols, and so that's where you arrive at something abstruse like this. Where we have P and Q and then some symbol in between both of them. And we know, because there are only 16 truth tables, that we have all possible situations here. Now, I'm going to come back about that, but of course, you will say, if we have that, what if we do have a P, a Q, and a lot of other input functions or elementary or atomic statements, P, Q, R, S, T, and whatever? What's the implication here? Said we've got for two binary input variables, we have 16 truth tables. With n binary input variables, we would have, my combinatorial logic is not great, but it would be something like that. I got it from Wikipedia. I wanted to check it, but I think it's correct, the formula. We have a double exponentiation, 2 to the power n. So with 2, that's 4. 2 to the power 3 is 8. 2 to the power 4 is 16. And you see it's 32. It's very ugly what I'm writing here, but hey, this is a 4-bit, 8-bit, 16-bit, 32-bit computing registers. Is it that? Well, yes, it's that. Uh, for me, this was a bit of an aha at Leibniz because 30 years ago, I think I passed my exam in formal logic just with a 10 or an 11 because I wasn't really interested. Um, but now I see the light. This is really interesting because, yeah, if we have three statements, it means we can logically combine them into 256 possible truth tables. Having studied again a bit of physics, quantum physics, this makes me think, okay, we have base states, but yeah, I use base states a bit wrong here. We have elementary statements, and these combine in sort of 256 possible combinations, I would say, and we can reduce this to these base states. I'm using base state. I mean, any physicist will tell you that's not what a base state means. No, it's not. Base state of a system is basically, yeah, in a system of equations, you can yeah, I'm not going to go into the detail, but we would have a lot more base states than 256. But in this cosine of system, you understand what I'm saying. We have basic inputs, and we have 256 possible states of the world, I would call them. And we can represent them, and this is the interesting thing, to represent 16 possible states of the world. We would need a nibble, 1, 2, 3, 4 bits. Because then we have value from 0 to 15, 16 values in total. If we have a 1-bit world, as I call it, just one statement, yeah, it's 1 bit. It's a 1-bit world. And that bit is either 0 or 1. It's true. The world is, or the world is not. Because your statement probably would be P, the world. Let me clean up my whiteboard again. That's a PDF whiteboard because my internet connection is poor. So I can't use Microsoft or Bamboo Notes. With three statements, we have a byte world, and in the sense that we can represent all possible states of the world, states that may be or may not be true. By yeah, 256 possible states. So we have we need a byte for that. 8 bits ranging between 0 and 1111111. Yeah, and so it goes on and on and on, and it gets quite ridiculous. This is what you're seeing. It gets quite ridiculous because with 5 statements, we need 32 bits to represent all possible states, and 32 bits will give us 4,294,967,295 values. With 6 input binary, we are going to be talking about 64-bit words, I would say, to describe one state, and we have 18 point something with 18 zeros behind it. So yeah, you see, we have I talked about it. We have a lot of computational power, but we can have 128-bit words and computer words. This is sort of where yeah, this thing where you say of, okay, well, we can model the world in terms of a number of base states and then combine them. Well, you're never ever going to have the computational power, and it's also going to be quite a meaningless exercise to sort of say like, well, we need 2 to the power 256 values or words to understand what the state of a world could be with only 8 inputs. This is where I said that this quantum logic and computing law, I don't get it where they wanna go, because it doesn't make sense. And that's where Wittgenstein's TLP, the Tractatus Logico-Philosophicus project, went wrong. And he admits so much. I talked a little bit about that in his later letters. Wittgenstein basically went crazy, yeah? Where he had to admit that you know, logical systems are actually always they have some ambiguity, and you need to allow a multi-valueness. You see it even in mathematics, I think. Derivations sometimes need a very innovative way of coming up with a new equation. The one I wrote here, or I didn't write it here. Oh yeah, no, I didn't. The one on the four vector notation of Maxwell's laws needs at some point in time a choice, and that's a choice that probably no computer could think about it. It needs a Lorentz gauge, and it's sort of kind of an innocent operation, but at the same time it provides a sort of an anchor um, for that logic. And without that anchor, yeah, you just sort of discover it. Without that anchor, you are here I am. You can't do the trick. Again, to be positive about formal logic, that's not again how we think about proposition. How we should be thinking about propositional logic. We will analyze statements indeed. PQR with three statements. What was it? How many values I needed? Yeah, 256. No, we will analyze indeed these things in terms of the original P and Q, and we will combine. We will reduce the complexity by, combining them in substatements like this: P with an exclusive OR with Q between brackets and R. And so we will not invent some new logical operator when we go from a two input to a 3 input system. So yeah, the exercise is meaningful and at the same time meaningless. I will think you about yourself, how meaningful it is. I think it is meaningful because, again, the thing that impresses me most is indeed that these artificial intelligence has moved very fast on learning. It's the best kid on the block, I would say, in terms of going to school and learning how to speak. Can switch between languages, between formal systems of representation. It is amazing. And at the same time, ChatGPT 4 can read and parse. I talked about it. Really, papers, I think maybe only a few people understand. I mean, the one paper I gave, it had 14,000 reads in a fairly short period of time. So even if I'm a weirdo, that's, again, I'm talking to my brother here. You once said, Jean-Louis, the difference between a genius and a madman is that a madman babbles in the corner and no one listens to him. A genius babbles in a corner as well, but there's people surrounding him and listening to him. So people are listening and reading those papers. ChatGPT just does it so much faster and parses that logic. At the same time, it fails like on the big picture issue on that paper. But that might be fixed in a year or 2 years, and then you really wonder. And here I'm gonna draw that exponential curve. This is what is happening now in terms of ChatGPT or other AI systems really understanding something. They're still not there's this really tiny margin where I said for me it was in my interaction. Does this thing really understand Schrödinger's equation in the way I interpret it, and why I think it's better than Klein-Gordon? But that margin is becoming smaller. The investment that will be needed to bridge that margin is smaller, but it doesn't matter. That margin may stay small or large. The thing is, it's not gonna hit a wall. Why not? Because the only wall it can hit used to be computational resources, right? And these, that curve has gone up exponentially as well. So computational resources and this kind of complexity of these artificial intelligence systems. It's not going to hit the wall. The sky is the limit, and that's not scary. It's a brave new world, but it's going to be fascinating to watch over the coming decades. So yeah, I'm done with it. I'm going to go biking now. Um, I wouldn't have done this presentation in summer because it's a bit cold to go out, but I'll go out now. And I'm at exactly at 1 hour, so that's great. Bye, Jean-Paul. Good luck.